Hello, everyone, and welcome to the Module 5 Python exercise. In this notebook, we're going to be walking through the k-means clustering algorithm. This one's a little bit shorter. K-means is pretty straightforward, and honestly, a lot of it is up to you to kind of play around with it. As I mentioned in the slide video, the lecture video, k-means is one of my favorite algorithms to play around with because it really is one that you can play around with. You are going to try it out, think a little bit, and then try something a little bit different. So while you see my notebook is set, I've got all the variables in, I've got my algorithm kind of done. That doesn't mean that I didn't play around with it quite a bit as I was creating this. So don't feel like you do the algorithm once and then you stop. This is truly one that you should be creating quite a few k-means as you go through to see what works best. And I'm actually going to restart my kernel. If you ever need to restart your kernel so you can clear the outputs, like your line numbers, you want to just restart that, clear all your variables. Just a reminder, you can do that by going to kernel, restart, and clear all outputs. I just want to get a nice fresh start. And then the other reminder I wanted to tell you about, I have some of these cells. They're called markdown cells. So if you're ever in one of these and so you see up here it says code, you can manually change this from code to markdown. And then if I run it, you see how it's now that markdown. That's like the text instead of the code. I'm going to change it back to code. So if you double click in here, you can see how I've formatted it. I can put in links, I can put in pictures. It's really, really neat. So you can always do regular just comments, but if you ever want to add in nice headings, especially if you want to view and look at the table of contents over here, you see where you can just click on different pieces of the code, which is really neat. I love it. The markdown part's really nice for that. I have gotten really fast at this because I just insert a cell, and then the shortcut to do this is escape, and you don't have to hold them all in. So escape, and then M, and then enter, and it changes your cell. You saw that it automatically changed to markdown. And then I think if you want to change it back, it's escape C, enter. Nope. Actually, I don't know. Let's see. I don't know I don't really do the opposite very much, but the shortcut to change it to a markdown really quickly is escape M, like the letter M as in Matt, and then enter. So that's my little Python tip for the day. So in this notebook, we're going to be starting out with the iris dataset. That's one that you've probably heard people talking about in general. It's a really popular data science dataset. It's really tiny. It's only 150 observations. And I'm going to go ahead and run this because I talk about it a little bit later. It is very, very common. And this is it is one of the first ones I saw that made me have that aha moment that I wanted to be a data scientist. I saw actually this exact exercise, years ago now, and I just had this fascination with this data set, and I thought it was incredible that you could do this kind of thing. So hopefully you do as well. As always, we're going to import our packages. And I left a little tip here. I had a few questions about when do you use the read CSV function? When am I using this funky code? So this, when I'm importing from the UCI ML repo, that is when we are utilizing the UCI, the UC Irvine Machine Learning Repository. That is just these very nice people at UCI. They have provided data sets for us where we don't have to deal with files. It's just available online, and we can import it into our Jupyter notebook without having to deal with Excel. So I have this to start. I do have an example at the end that I'm not going to go through in detail, but just if you want the code to do it with an Excel file, that's where it is. And when I say Excel, you want to use a CSV file. And my other tip is that you do not want to use a CSV file that you have opened on your computer if you can avoid it. So if you have to make any edits, save the file, make sure you don't touch it afterwards. Python can be really iffy with Excel files, CSV files. It can do some kind of weird things. So the CSV file that's going to be on Brightspace, don't open it. Just save it to your computer and then import it into Python when you're doing these exercises. That will avoid a lot of issues. So we're going to say UCI, hey, can I use your data set? It's called, I'm just going to name it Iris, but it's ID number 53. And they divide it up kind of not oddly. It's nice for a lot of stuff they do into X and Y. I want it though into a data frame like we normally use, and I always call it DF. So that's what this piece of code does. I didn't use it in module 1 because I honestly just learned how to do this. The UCI repo, I don't know if they had this a couple years ago when I taught a similar class. They keep updating the repository. You used to have to download the CSVs every time. So it's really nice that you don't have to do that all the time. Anyway, I'm going to stop rambling and start going. So we've imported our data, and now we're going to get down to data cleansing. I'm going to leave this in here for you to read, but if you want to know more about irises and the different parts of an iris, this is going to help you out a little bit. So let's view our data. So we've got class, and these are the different types of species of iris. The sepal length, so this piece, the sepal width, the petal length, and then the petal width. So we're looking at different parts of a flower. And as I mentioned in the slide video, we're going to look at clustering, so unsupervised. In the description, you'll see that this data set's actually really popular for classification as well. But you'll notice in a bit that it works really, really well for clustering. So that's why we're using it here. It's a really great example data set, and we'll get down into the details of a more common example of clustering at the end in example 2. So when we look at this, of course, we have the one thing I will note on this data set is that we have a column called class that is has a text field. Remember that k-means does not do well with text. And in fact, I really don't want this in my k-means model. So I'm going to have to do some things later to make sure it's not in there. So it's actually kind of good that I have this x and y. I'm going to have to use that later. So I've got my x and y. If I'm looking at this, I can kind of get a good view of my all my variables. I've been really liking these correlations to start. I get in different moods as a data scientist. Sometimes I'm in more of a visualization mood. This month I've been in a really big correlation mood. So let's look at these. And this is one of the instances where that x variable is really nice for us. We can just say, look at the x variable and look at the correlation. So obviously across, we're all going to have ones because sepal length and sepal length, it's going to have a perfect positive correlation. Interesting though, if you start looking at these, so sepal length and petal width, they have a pretty strong positive relationship. So as sepal length increases, so as these get longer, the ones that fall to the side, the ones that stand up get taller and wider, typically. The other one that I saw that stood out, as the petal width gets wider, the petal length gets longer. So typically we're not going to see really skinny long petals or really wide short petals. The petals are going to be typically, they're going to grow as they also widen. So it's interesting to note. The negative relationships we see are petal length and sepal width. So we typically, as the petals get longer, we have a narrower sepal. And I have no idea if I'm saying that right. I've never heard anyone say it out loud. Let's plot the data, see what we're looking at. So sepal length, sepal width. And remember, we're doing clustering. I immediately see a nice little cluster here and maybe something here. Interesting. Maybe if we add in some additional details, we can start to see. And that's exactly what we see here. So when we add color and we add the class, so which species it is, to the scatter plot, we can see that this one over here that I pointed out, that's an entirely its own species. And then the versicolor and virginica, they're all kind of mixed in here with the sepal length kind of all spread across and the sepal width all about the same. Okay, so let's move on to petals. Let's see what's going on there. Look at that nice separation. So that setosa, I know immediately that it is very distinct. It's got really teeny tiny petals, and it's got really short but wide sepals. So it's got some really nice separation. The versicolor, on the other hand, varying sepal lengths, but a pretty consistent width. And then on the petals, it looks like it's got some decent separation here. The petal length is typically a little longer on the virginica, a little bit shorter on the versicolor, but we might have some trouble here just because you notice how these are kind of intersecting. Now, on a classification problem, we could probably handle this no problem. Just picture all of the models that we've built so far. You could probably build a decision tree, any sort of model that could handle this no problem. But since we're doing clustering and we're just trying to say all of these are a cluster and all of these are a cluster without actually telling the model this is what we want, we might have a little bit of issues separating out some of these. But my hypothesis, now knowing that I already know the answer, is that the setosa is going to be solid. We are going to be really good at this. Now, moving on to the actual k-means clustering, it's actually pretty straightforward. So we're going to normalize the data if it's needed. For this case, because we're looking at all the same scale, they're all length and width in centimeters, I'm not going to need to normalize the data. Example 2 does have a normalization method, just so you have it. I'm going to determine the number of clusters, which is k, run the algorithm, interpret the clusters, and assess the validity of the clusters. Now, this assessment, that goes back to the business case, so we won't go into details on that in this notebook. That is more a conversation for you and the business. And when I say the business, that's whoever you work for. That can be an education, nonprofit, a sports team, whatever you are doing, whatever purpose you are serving with this clustering algorithm. That's where you're going in here and saying, does this make sense? Is this meeting our use case? So we are going to import our module, importing cluster. And then we already know there are 3 species of iris, but let's try the elbow method anyway. The way this is set up, the only thing you will have to change on this, probably ever, is if you want more than 11 clusters potentially, you would have to change this 11. You will also eventually have to change this X. You will have to change it to data frame or normalized data frame. And again, I have an example later. I got this really great code from Statology. It's already set up. I'm not going to go through a ton of details, but basically it is saying, let's run k-means with 1 cluster, and then let's run it with 2, and then 3, and 4, and so on. And we're going to continue trying that and see what's the sum of square error. Basically, remember, we want the clusters to be separated from each other and tightly knit within each other. And when we run this, again, the code is beautiful. It's already put together. We get this nice little elbow chart. So that first little dip is not what we're looking for. We're looking for this one right here. And that gets us right at 3, which is exactly what we wanted. But remember, the business case is right along with us as we're looking at this elbow chart. So if the business case says we want 5 and the elbow chart says 3, maybe we go with 5. Maybe we go with a nice in between. Maybe we talk to the business people, the people that we're working with, and we try to figure out why is it 5. These are, yes, the mathematical, we should go with 3, but that's not the end-all be-all. Clustering is made for the business case, the case that we're working on. This is not a, you have to choose 3 or else it's wrong. This is, let's group the data and see what happens. We're going to There's a word for this that I can't actually say. It's instantiate. I think I maybe got it. We're going to say, I'm going to create k-means. And it's just like the predictive models where we say, I'm going to create a decision tree, but not actually give it the data yet. So k-means. So I'm going to call k-means, and I'm going to say I want my number of clusters to be 3. And I'm giving it a random state, just like I did with my modeling and my train test splitting, because k-means picks some random starting points, and then it finds the clusters from there. By giving it a random state, we all get the same answers, and we get the same answers every time we run this, which is nice. So k-means, and then I'm going to fit my x variables. Remember, because we've got the species in my data frame, we don't want to send the full data frame, so we're just going to fit the x. Now, big important thing here, if you end up changing your data frame order, you do some funky things with changing up the rows or anything, this will end up breaking your data frame. Because I have not done anything crazy with my x and y in data frame, I have just said x and y, smush them together, and that gives me my data frame. This works. If you somehow start randomizing your rows or you filter out your data frame, this is where that will break, because you'll suddenly have more rows in your x than you do in your data frame df. So just make sure you just keep it on the same scale. Make sure it always has the same number of rows. So let's run this. And it pops up like this. It doesn't really say anything. I'm going to run this little piece to say what's my silhouette score. So that's the elbow method. The fancier name is the silhouette score. And there are lots of scores that go along with this. This is just kind of, the elbow method gives us one nice little metric. This 0.55 though, this doesn't really tell you much unless you start comparing it to other runs of this exact same data. So it doesn't really make sense to compare this 0.55 to a completely different data set where you've clustered with 7 clusters. It would only make sense to compare, let's run it with 3, and then let's run it with 5 with this exact same data set. The other piece here is this metric. That's where I mentioned in the slides we have that distance metric, and you could use Manhattan distance, which is like city blocks, but a common one is Euclidean, which is as the crow flies. So if you picture, your house to UND's campus, but if you didn't have to use all the roads, that's how the crow flies. Anyway, that's the mathematical piece. We get 0.55. Lower score is a better fit. We can look at the cluster assignments by calling k-means, which again is what we called that model, dot labels with that little underscore. Don't forget the underscore. When I run this, though, you see what I get. It's just 1s, 0s, and 2s. That's just the cluster assignments, which that doesn't really mean anything to me yet. So I'm going to say, let's create a new column called cluster, and I want it to equal the k-means.labels underscore. And that's again where if I had changed some things in my X or changed some things in my data frame and removed rows or anything, it would not work like this. But because they're still the exact same, it works fine. I can run this, run that, and now I have this row at index 0, my cluster's 1. 1 is 1. And let me run tail just so you can see it. Beautiful. You can already see some issues, but that's okay. And now we can start to actually analyze this. Did it actually separate the irises into their different species? Remember, this was unsupervised learning, so the machine doesn't know that there are different species. It's just looking at these 4 data points, sepal length and width and petal length and width, and saying, how can I group these into 3 different groups? So you see here that one that I said was going to be perfect, it was. Setosa, cluster 1, 50 for 50, perfect. It absolutely nailed it. Versicolor, so 3 of them ended up in cluster 0, and then 47 of them ended up in cluster 2. So the majority are in cluster 2. There are a few that ended up in cluster 0. So that's not too bad. Virginica ended up a little bit more rough. It was mostly in cluster 0. It just starts numbering at 0. And then some ended up at 2. But if you grow up here, that's where we're going. So that's where there's that overlap. That overlaps. That's where the k-means algorithm, there's just so many that are kind of similar. It couldn't really separate those as well. That's okay. This is the unsupervised learning part. It separated it as well as it could. And we can actually visualize this using principal component analysis. Remember, that's the bonus content for this module. I took it out of the full module. So I'm not going to go through this in detail, but this basically takes all of our variables, in this case 4 of them, and puts it into 2 variables so we can see it on a 2-dimensional chart. So let's take 4 variables and make it into x and y, and then let's visualize that. And when we do, you see these cluster assignments. So this is 1, which ended up at, it should be Setosa. Yes, so cluster 1 is Setosa, and you can always rename these too. If you just Google pandas rename class variable, something like that, you'll get exactly what you're looking for. I would show you, but I just realized I'm recording on just one tab. But then you can change that 1 to Setosa. So you see where that is nice and neat right there. And this is where we're struggling here. So that's that one little area. The algorithm can definitely tell these apart from these, but there's this center area where it's like, I can't quite tell where the separation is. So again, remember, this is a 2D representation of 4 different variables. So it's not a perfect view, but this is using principal component analysis, which is pretty neat. So that is k-means in a nutshell. I'm going to very, very quickly go through the second part just so you see what's going on. This is using a data set that's on Brightspace, so make sure to download it. And we're going to do some customer segmentation. And I'm going to limit it to just a few columns so I can show you what's going on. I am dropping the columns I do not want. This one had a ton of columns. I just wanted to limit it to a few. So I've got income, wines, fruits, meats, fish, sweet products, gold products, purchases made with deals, total, and then regular products. This is one I mentioned, so I'm using a CSV file, so I don't have my X and Y, but this one has all numeric values. So I don't have X and Y to fall back on, so I can just send the data frame because it's numeric values only. But you notice, since I've got income and also amount spent on fruit and wine, I'm going to have to scale this because this makes no sense to plot on a scatter plot and do a mathematical distance. I need to normalize that data. I personally like a min-max scaler. I like putting everything on a 0 to 1 scale. So here's how to do that. You import it, you start your scaler, you fit it to your data. You say, this is going to be my scaled, and then I like to put it back into a data frame, and that's what that looks like. So I've taken this data frame, and now it looks like this. And this kind of just confirms that everything's now on a 0 to 1 scale. Nothing odd going on. Looks good. Now I'm going to run the exact same thing that I ran earlier to get that elbow chart, except now I've got that DF norm instead of X here. Everything else is the same. And when I run this, so I get that first initial drop at 2 still. Otherwise, I get something here at 3 and I get something here at 4. So this is where you can kind of debate, and that's actually a typo. That should be 3. Oops. So you might say 3 looks best. I might lean towards 4. But this is where I mentioned the business case rules all. So there's a slim margin between 3 and 4. So you're not gaining a ton by moving to 4 clusters, but maybe your team already has 4 treatments in mind. Maybe you'll analyze the data and see, ooh, 4 clusters just isn't good. I want to move to 3. This is where I mentioned here, and I wish I could highlight this, make it huge. Just pay attention to this. K-means should not be run once and forgotten. You need to run this over and over and over to find what makes sense for your case, whatever you're working on, your research project, your goal, whatever it is that you're doing. This is an unsupervised process, but you are very much involved in it. So, off my soapbox. We're going to do the same thing that we did earlier. So, K-means, we're going to do 4 clusters, fit it, and then I'm going to create my variable with clusters. I'm going to then visualize my data using PCA. And you notice here, so when I did this earlier, I got some really nice separation in one cluster, and then the other 2 were kind of together. This is a small data set, and irises are pretty easy to tell apart. People, though, are not so much. So you see here, yeah, there's a little bit of separation when I add the colors to it. Realistically, though, yeah, there's some difference, definitely some separation. I can see I would have probably drawn something here, something here, something here. I don't know for sure I would have separated right here. So maybe 1 and 2 are pretty close. I would assume that cluster 0 is going to be pretty different than cluster 1. Cluster 3 is probably going to be the most different than... That one's really spread out. That one might be kind of a problem cluster. But this is a good one just to kind of get a gut check of what's kind of going on here. But you're going to need to dive into some of the details. And I ran this because I forgot what columns I used already. I like box plots to look at some of these. So let's see income versus cluster. So I see that 0 and 3 are the higher incomes. 2 is a little bit lower, but some higher earners up here. Cluster number 1 has some lower income earners. So that's something to kind of keep an eye on. That's something that stands out. And that's what I mentioned about over-indexing or under-indexing on the slides. This is what I'm meaning. It's something that stands out as, cluster 1 might be a little bit lower income. Let's look at wines. Cluster 1 does not like wines. Cluster 0, though, they are into wines. Cluster 2 and 3, about the same. And this one, again, I'm going fast. Fruits, cluster 3 is into fruits, okay. Not so much cluster 1. I'm going to remind myself which one was cluster 1. Okay, so that's this tightly grouped area right here. Okay, let's go to meat products. Not a ton of separation there from these. 0 has a little bit more meat. 3 has a bit more. 1 just no meat, no wine, no fruit. What about fish? Ooh, 3 likes fish. Okay. 1 still does not like any fish. So purchases made with deals. This is interesting. So 1 is the lower income, but they're not making many purchases using deals. 2 is, though. So even though 2 has kind of the higher income, they're not using deals as much as the lower income group. And looking at the total, obviously 1 is going to have the lowest because they have not been purchasing anything I've been looking at. 1 is the highest, 3 and 2. And then you can look at some descriptions. And then when I talked about validity, this is where you can start to kind of have fun with it. So, cluster zero, I observed that they are a high spending group who purchases a lot of wine compared to other clusters. So, you should target them for high end wine, maybe some, try to get them to purchase more of the cheese and meat kind of things because they are purchasing meats, but they have a higher income. They like wine. Try to pair that up with something maybe. If you look at cluster one, they are low spenders with lower incomes. So that immediately makes me think that they have price sensitivity. They also were not looking for deals or they didn't use deals. So they might not be ones that look for coupons or maybe they don't even know about it. So that might be worth looking into. Are they checking out the website? Are they signed up for emails? How do we reach them to really see what are they doing in our data set? Cluster two, those are the deal seekers. So even though they're still higher income, like clusters zero and three, they spent more using deals, or they utilize deals more often. And then cluster three, they really liked fruit, and then they also really liked fish, and then slightly more meat than the other, or slightly less meat than the other clusters that also spent a lot. So I hypothesize that maybe these are more health conscious, so maybe going for healthier meats, lots of fruits. They didn't really drink a lot of wine, so maybe go for some health conscious marketing, or maybe just keep in mind that they might be more health conscious. So this is how clustering is used. Oftentimes, it's used in marketing because we want to start to get to know our customers, and it's really hard to get to know them one on one. So we do this at a larger scale. We get to know groups of them. Remember, K means will always give you some sort of answer, but that doesn't mean it's always the best answer. So we want to make sure we run it multiple times, we analyze it from multiple angles, and we always go back to the question of what are we using this for, and does this make sense? If you would like to learn more about principal component analysis, there are some optional readings and videos on Brightspace. Next week, we're going to be focusing more on your final project, so a lot less coding next week. I'm going to be mostly talking to you about model deployment and how to really start to organize your project and get honestly close to the end of the semester. And with that, have a fantastic week. I will see you next time. Bye.